So we just discussed how hard it would be, and that we would have to rederive the whole ordinary differential equation from scratch if we were to consider motor times other than permanent magnet DC into a motor sizing study using MATLAB alone. Now, there are some additional studies we will be running into hindrances if you use MATLAB alone as well. One such case would be the addition of a gearbox. Now we can add the gearbox to increase the torque of the motor output while reducing the RPM in a inversely proportionate manner. Well, a clever person, by careful observation, can modify that equation we have previously obtained in order to reflect the effect of a gearbox. However, this is not the recommended or the standard means of doing it, and it's quite an ad hoc method. So the standard method would be to rederive the equation from scratch. So this once again highlights the lack of flexibility when using MATLAB alone to make modifications to the already existing differential equation for the model of a system. And if we were to consider previously unconsidered torques as well, for example, the torque due to air resistance, once again we would have to obtain an expression for air resistance and rederive the E to include the effect of that as well. So let's look at the first deficiency that I have listed over here. So I have stated that the model I have used for motor torque is incomprehensive. Let me explain what I meant by that. Now, if you recall the relationship or the curve that we saw uh, in the data sheet for the 775 motor, the torque versus RPM curve was something like this. So it was a linear curve, but go back to it and observe the fact that it did not extend beyond the x and y intercepts. But the equation in the form that we obtained was a y equals mx plus c1. The typical equation form we would have for a linear plot or relationship. That kind of equation would not be limited by mathematics to this particular domain. So if you were to take y equals mx plus c and plot it over the whole range of theta dot for negative values of theta dot for negative values of RPM or the angular speed, it would uh, the expression would output that it would have higher torques than the one provided at stall point. So now in the real case, a torque output like this is not really available, and it's not really possible. And the mathematical model that we implement would have to enforce this limitation by keeping the torque output within these particular limits. And the detrimental or the false result that you obtain by the lack of this comprehension in this model can be observed if you can run case C for more than 0.2 seconds. For let's say if you run it for actually 2 seconds, then you will be able to observe some spurious action with regards to the curve, and that would be the effect of having such an incomprehensive model for the motor torque. Now I can enforce the limit that we require in MATLAB as well through some clever mathematics. However, it would be much easier to do in Simulink, and you can specify the torque limits without any without resorting to any complex or tricky mathematics. So that's an advantage of using software provided by MathWorks other than MATLAB in the domain of mechatronic systems modeling. And we'll discuss some additional motivating factors which drive us into such tools which are better equipped for handling modeling of complex systems. And one such factor I have noticed is that when using MATLAB alone, it's an extreme hassle when it comes to obtaining plots, weaving data, and so on and so forth. If you take a look at the code that we discussed in lecture 3, you'll see that each time I want to have a plot, I need to open up. Within the code, I need to specify statements for opening up a figure, for the labels, titles, X labels, X and Y axis labels, regions, and so on and so forth. It's quite an unnecessary housekeeping work when you have multiple such plots. And you'll notice that when you move on to more better equipped software like Simulink or Simscape, obtaining plots whenever we require would be made much easier than that. And they also provide such a feature called live plotting, where the plotting would be done in real time. So if we were to run a simulation for 10 seconds or so, the plotting operation will happen for the whole for the whole 10 seconds, and you'll be able to see the results being plotted in real time. So let's finish this video for now and move on to using Simulink to develop or re-implement the model for this simple mechatronic system.